Hello, it's Keith here, and this is lesson 3 of the Photon series of 650 assembly programming tutorials. Well, what's Photon? Well, it's this massive game you can see over here. It's basically a Tron game, if I can remember my controls. No, I can't. Yes, I can. It's a very simple game, really. You play against the computer, and you've got your classic life cycles, a few simple obstacles. Really, the game is it's a demonstration of how to do pixel plotting, line drawing, and pixel reading. So whereas before we'd been doing bitmap graphics, which were just sort of sprites and things that were copied as blocks by bytes, this is actually working at the pixel level, and that's especially tricky with the Apple II, because the Apple II is the only system I've ever heard of that has 7 pixels in a byte. There'll usually be 8 pixels or 4 pixels, not 7. So yes, that caused quite a challenge for me, and we will discuss that in just a moment. So that's the game. Let's go over to the code and let's take a look. Okay, so the first thing the game does is it's defining the size of the screen. Now the screen is 280 by 192. Why 280? Well, 280 is 40 bytes wide times 7. Because there's 7 pixels per byte. If you're wondering why there's 7 pixels per byte, please see my bitmap examples, because the 8th bit is actually a color attribute. You see, the system has these sort of NTSC colors where certain combinations of pixels will have a color. It's kind of garbled a little bit, but it can do it if you work in pixel pairs relatively well. I did that in Grime and YQuest, I believe. And it can do that fairly easily, and the extra pixel will define between 2 possible palettes. I've not done that in the case of this game. They're quite clunky and ugly at the best of times. I thought we'd just stick to black and white this time, but that's where that extra 8th bit goes in each byte. So our screen size is 280 by 192, and as I say, I'm just treating this as black and white. Now the game supports up to 5 colors, a background color and 4 others. In this case we haven't got any, so we're just mapping them all to color 1. The game will work just fine like that. And then we've got some initialization for our screen mode here. I'm going to skip over this because we're going to discuss this in just a moment. We're initializing our memory. We need about 256 bytes somewhere. We're defining them just here. That's our game memory, showing the main menu, and here is the main loop. So how does the game work? Well, the game basically has a few little quirks we need to discuss for the code we're about to see. The first is that there is something known as boost mode for the player, and this is where the player moves twice the speed of the enemy. This is so you can catch up with the enemy and try and sort of slam into them and things, you know, just to give it a bit of a challenge. If I press fire, I'm now moving faster and the counter's going down in the corner of the screen. That's one thing to note. The other thing is, if I press the left button and hold it down, I only move once. I have to release and press and press and press, and that's so that we don't immediately collide into ourselves if we hold the direction down. So we're going to see that in our code here. That's why we're showing it. Okay, so the first thing is the tick. Now the tick is either 1 or 0, and in boost mode you move every tick, in non-boost mode you move every other tick. We then have a delay loop here. It's either going to be 30 or 1. Now the reason we have a delay loop is firstly we just need to slow the game down a little bit, but also if boost mode's on, we have to update that boost counter, and it's a vector font and it's not very fast to draw, unfortunately, so we're having to alter the speed of the game to compensate. So that's what we're doing there. What we're doing next here is we're reading in the controls, and we're going to store any directions in a buffer in 0 page entry D here. Now if a key is pressed, then we're going to store it in ZD, but if a key is released, we're going to 0 the timeout and clear that buffer, and that's because we need to make sure that if the player was still holding down the key, we're going to ignore those key presses. So that's how we're dealing with the key presses there, and we're just looping until the delay reaches 0 there. Now when we get here, we're going to check if the key timeout is still set. If it is, then the player never released a key, so we're going to ignore whatever's still down, and we're going to skip over the next section. What we do next is we set the boost value to 1, and that actually means off. 1 is off in this case, and we turn it on down here by writing a 0. We're then loading the player X acceleration into 0 page entry marked as IX. Now what this is the movement speed of the player, and also effectively the direction. So this will be changed by the set player direction function, so we need to load IX in anticipation of that. Now what we do next is we're checking the directions read in up here by this read controls dual function. We're not going to cover that. It's exactly the same as in YQuest and the simple series, so I really can't cope with teaching it another time, so please see those if you need to know that. So we're checking the joystick directions. We're checking left here and right here, and we are either decrementing or incrementing the player direction. There's 4 directions, north, south, east, west kind of affair, so we're just going around those. The inc and dec will move the direction, and then set player direction will limit those to 0 to 3 and read in the new accelerations and write them to the specified value in 0 page entry IX. So that's how we're doing that. What we're doing here is we're checking if the fire button's pressed. If it is, we're checking if the boost power is 0. If it's not, then the player can use boost. We're setting the boost value to 0. All of the actual boosting, if you want to call it that, is done by the handle player routine, and the CPU routine does all of that kind of thing. And this also includes collision detection, CPU AI, all that kind of goodness. It's all multi-platform code. This is just the platform specific stuff. And once we've done that, we loop back up to the top. So there we go. I say we're not going to cover the stuff I've covered many times before, so the joystick routines we're going to skip over. It's going to be the drawing routines I want to focus on here. The PSET and the point. PSET plots a pixel, point reads one, and it works in individual pixels, not in bytes. So we're going to specify a 16-bit X position and an 8-bit Y position, and so we're going to use A and 0 page entry B as the X position. The reason we're doing it like that is because this is to match the Z80 version. It uses the same registers as the 0 page entries in this case, so that's what we're doing there. So we got a function here called getPixelPos. This will take an XY coordinate and it will return a memory address in DE of a screen byte, and it will also return a mask for the background because there's going to be 7 pixels and we're going to need to keep 6 and change 1. So the 0 page L entry is going to be the mask to keep the background, and the H entry is going to be the bit to set the pixel we want to change within that, and it's going to all be calculated by getPixelPos. So here we are testing the value in D, which is going to be our color, 1 or 0 in this case. If it's a 1, then we're going to set it by ORing in H. If it's a 0, we're just going to clear it by keeping only the other bits here using this L entry here. Whatever we do, we're saving back the value back to the screen. So there we go. That's how we're doing things there. So that's how we are setting a pixel, and the reading of the pixel is almost the same. We're using this getPixelPos function here. We're then going to get the current screen value. We're then going to mask it with the mask for the pixel we want to look at. If the result is 0, then the pixel isn't set, and so we're going to return that 0. If it's non-zero, then the pixel is set, and so just for consistency, we're going to return a 1 here, because otherwise it would return a different value depending on the position that was set. And on the other versions of this code, we return a color. So we want to do the same kind of thing here for consistency. So it's quite clear that really all the clever work is being done by getPixelPos. Really, these are very simple routines here. Now the problem is that our getPixelPos is going to get an X coordinate from 0 to 280, and it's going to need to work out a byte coordinate for the memory that we want to change, and also a pixel within that byte so that it can work out the masks. Now it reads in the masks from a lookup table here, so these are the masks for all of the pixels, the position of the bit that affects the pixel. You can see that actually is reversed there, which is very weird. Why everything seems to be so weird, I don't know, but it is, so that's what we've got to deal with. But what we need to do is basically take the X coordinate and we need to divide it by 7, because there's 7 pixels per byte, and the whole number part will be the byte, and the remainder that couldn't be divided in whole numbers will be the pixel within the byte. So we need a way of dividing and getting a remainder, and there's 2 potential options, and I will show you the first one I tried first. So I've got a little function I wrote for Chibi Aliens, and it's been I've been playing around with it ever since. It's a little division routine, and it's not great. I'm not going to cover it here because it's not good enough, but it does work. So this div16 will do a 16-bit division of the accumulator here, and it will return a whole number division and also a fractional part. So that's what we're doing there. Now what I can do here, if I run this code, is we can see this in action. So this is using that division routine. So this is calculating the division on the fly. It works, you can see it works quite well, but boy is that a bit slow to draw. Now the game will actually be okay, because once the game starts, well, I mean, there's still going to be the boost mode, which is going to be, yeah, that's pretty horrible. So yeah, that's the problem. It works, but it's slow doing all those calculations, and that's because we're having to calculate these divisions every single time we want to plot a pixel. Not good. So what's the solution? Well, the solution is to calculate all possible 280 divisions in advance, because we need a byte part and a remainder part. So if we allocate 280, because the 0 to 279 x coordinates, times 2, 1 byte for the whole number part and 1 byte for the remainder part, and we calculate all those divisions in one go, we can then read those divisions from the lookup table, and that's what this bit at the start does that we skipped over. So we're using X and A here, and A is the whole number units, the bytes for the screen position, and X is the remainder part, which is the pixel within the byte, and we're just looping here, incrementing X, and that will be the remainder, and then when X reaches 7, we are then clearing it, and we are incrementing the accumulator here, and we're writing these to that array. So we're writing the whole number part first and the remainder part second, and so we're filling that memory array with the divisions in advance, so that when we want to actually use them, we can now do them a bit more quickly. And so here's that get pixel plus routine. I've now disabled the slow version, and here's the nice fast version. So what we're doing here is we're effectively multiplying the X position by 2 here, because there's 2 bytes per entry within that lookup table. We're then reading in a byte here, and the first byte will be the whole number part, and the second byte will be the remainder part, and the remainder part is the pixel, of course. So here we're doing those calculations here, and that's what we need to do to get the byte position and the coordinate. Now the byte position is being stored in ZL, and the pixel position is being stored in Y here. Now once we've done that, we're then going to look up the pixel mask from Y here using the pixel lookup here, this one, and we're going to store the mask for the pixel we want in D here, and we're going to then E all that, flipping all the bits, and store the mask for the background in E here. And so these we're pushing on as D here, but we're pulling back into the 0 page entry HL here, so we're swapping them over later on. But what we're going to do next is we're going to convert the X and Y coordinate for the byte into a memory address here, and that's what this is doing. This is exactly the same before as the one from YQuest. So again, I'm not going to cover it. It's converting an X and Y position into a byte on the screen, and that's how we're getting our byte position, and that's what's doing all the work. It's a pain. It took me a while to get working quickly. I can't think of a faster way of doing it. I don't think there's any way of doing bit shifts to effect a division by 7. If there is one, feel free to let me know. It's obviously too clever for me, but you can see that lookup table, you know, it brings the speed up quite nicely, although I would be lying if I said that the Apple II was my favourite system at this point with this rather strange screen. We will be looking at the Apple II GS later on, the 16-bit version with its nice screen. So you know, I'm not entirely criticising the Apple, but it does cause me some trouble in this case. Anyway, that's the end of this lesson. I hope you've enjoyed it. As I always say, you can go to my website and download today's example if you want to see it working, and you can get that division routine, although I do say the slow one isn't very well coded. It was a rush conversion, but it does work. Anyway, I hope you've enjoyed this. As I would say, if you have, please like and subscribe, because I've got to spend most of Christmas writing new tutorials, I think, and it's a bit of a pain. So it would really help me out if you like, and the videos get more views, and if you subscribe, it'll keep my motivation up while I'm trying to work out what to cover next year. Anyway, hope you've enjoyed this. Thanks for watching. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers, so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.